You are welcome to my physics class. Today, we want to have a look at part 3 on the topic current electricity. In this episode, in this part 3, we are going to discuss resistors in series and in parallel. How to calculate equivalent or combined or total resistance of all resistors arranged in series and in parallel. Now, I am starting with the series arrangement of resistors. Whenever you see resistors arranged horizontally like this, that means they are arranged in series. And what are the things you need to know about them? First thing, same current will flow through all of the resistors, even if they are millions in number. And what does that mean? That means current is constant. Therefore, if you know the current flowing through resistor 1, you have automatically known the current flowing through resistor 2, resistor 3, and others, if there are others. So that means the same current can be used for each of them. Number 2, potential difference, which is the same thing as voltage, across each of them will be different. That means the potential difference, the voltage for resistor 1 will not be the same thing as voltage for resistor 2 and will not be the same thing as voltage for resistor 3, except if the values of resistors are the same. But if the values of if the values of resistance rather are the same, but if the values of the resistances are different, then the voltage for each of them will be different. That is why I wrote this. V1 is not equal to V2, is not equal to V3. So, number 3, value of the total resistance. That means if you want to find the equivalent resistance or the combined resistance, adding all of them together, the result of for the total resistance will be greater than each of these one. For example, if this one is 3 ohms, this one is 5 ohms, this one is 7 ohms, the total resistance value will be more than each of them. That means it will be more than 7 ohms, which is the greatest or the highest here. So as we are going to see in the next step. Now, the next thing is, how do we calculate the equivalent resistance, which is also called combined resistance, which is also called total resistance? Let us go. Okay, total resistance, which I denote with R subscript T, for series arrangement of resistors, can be calculated by the direct addition of all the given resistances. Resistance in resistor 1 plus resistance in resistor 2 plus resistance in resistor 3. If there are more, you add them together. So as a result, when you add them together, definitely the result will be greater than the individual resistance. Okay? Now let's have a look at 1 or 2 examples. This is an example on resistors in series. Find the combined resistance of resistors 3 ohms, 2 ohms, and 7 ohms arranged in series. It's a very simple thing. Just say total resistance is equal to 3 plus 2 plus 7, and that is 12 ohms. So you can see that 12 ohm, which is the total resistance, is greater than 7, which is one of the resistances, greater than 2, greater than 3. So that was the last point I made under the note. Now let us have a look at parallel arrangement. Whenever resistors, two or more resistors are connected in this manner, that is vertical arrangement, as you can see, that is vertical arrangement, then we say that resistors are connected in parallel. Now, this is current I coming from the source. So when the current gets here, definitely this is a T junction. Look at it, T junction. So that means the current will be divided. So part of it will go here. Let me call that one I1. Part of it will go here. Let me call that one I2. And part of it will go here. Let me call that one I3. So now, what does this mean? This means that first one, different amount of current flows through each resistor. That means current that flows through resistor 1 is not the same thing as the one that will flow through resistor 2, and it's not the same as the one that will flow through resistor 3. So we have each of them we allow different amount of current to pass through it. The second thing you need to know is that by the time you add up all the current together, the current in each resistor, I1, I2, I3, when you add them together, it will give you this I that is coming from the source, which is the total I. This I is the total I, that is total I. Let me put it there. Total. So that means the total I is the current coming from the what? The potential, the voltage or the PD connected to the whole of this arrangement. Number 3, potential difference across each is the same as the potential difference connected to the whole arrangement. What this means is that the voltage across resistor 1 is the same thing as the voltage across resistor 2, and will also be the same thing as the voltage across resistor 3. Not only that, it will also be the same thing as the voltage that supplies this total current, because there will be a voltage that will be connected to the whole of this arrangement. When we get to the calculation under Ohm's law, you will understand this better. Okay, I am restricting myself to resistors alone today. So that means that is why I wrote here that the total potential difference, which is for the whole circuit, is the same thing as the potential difference for only R1, for potential difference for only R2, and potential difference for only R3. So that means potential difference is constant. That is the meaning. Constant. Now, the next stage we are moving to is how do we calculate the total resistance or combined resistance or equivalent resistance when we have two or more resistors arranged in parallel. That is what we want to have a look at now. So this is the formula. 1 over total resistance that we are looking for equals to 1 over resistance in resistor 1 plus 1 over resistance in resistor 2 plus 1 over resistance in resistor 3 plus, if there are many more, we continue to add them. So, but don't forget that after you have added them together, you need to make the RT here the subject because it's not yet in the right form. Take note of that. Now, having said this, let's go and have a look at 1 or 2 examples on parallel resistors. Now, this is an example. Find the equivalent resistance for the resistors 2 ohms, 3 ohms, and 5 ohms connected in parallel. So, you just remember the formula. 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Okay? So that means 1 over R total will be 1 over 2. Let 2 be my R1. 1 over 3, let 3 be the R2. And 1 over 5, let 5 be the R3. So by the time you find the LCM for 2, 3, and 5, 1 over RT will be equals to LCM for 2, 3, and 5 is 30. 2 in 30, that is 15. 15 times 1, 15. Plus 3 in 30, that is 10. 10 times 1, that is 10. Plus 5 in 30, that is 6. 6 times 1, 6. That means 1 over RT now will be equal to the addition of this, which is 31 over what? 30. Okay? But don't forget it is 1 over RT you have. You don't have RT yet. How do you not get your RT? Instead of you doing cross multiplication, which is the same thing, the faster way is turn this one upside down, turn this one also upside down. When you turn this one upside down, it becomes RT, which is over 1. RT over 1, which is RT. And then this one will now become what? 30 over 31 ohms, which can be taken to decimal. That's approximately 0.97 ohms. There is something I forgot to mention under parallel arrangement. If you noted the answer we got, you see that 0.97 is less than 2 ohms, 3 ohms, and 5 ohms. So have that at the back of your mind that the total resistance in any parallel arrangement is always less than each of the resistances given. Please take note of that. The answer will never be up to any of the individual resistance given. That will be a guide for you. Now, the next thing now is, let's have a look at combined resistors. Combined resistors means the arrangement, or let me say combined arrangement of resistors. Yes. That means we want to arrange resistors, both parallel and series. We want to combine them together in a single arrangement. How do we find the total resistance in such a case? Follow me. This is an example of a question on combined arrangement of resistors. Okay, if you look at this diagram, you will notice that we can section it into 3. 1, 2, 3. So this section, by mere looking at it, what arrangement is this? This is parallel. That means you will apply parallel formula to solve this. Then this is parallel. You will apply parallel formula to solve this. This is only one here, so we leave it the way it is. Now go and find this, the combination of these two using parallel formula, and find this one. Then let us meet and present our answers. I'm doing mine also. If your calculation is correct, this is the result for the combined resistance for this middle arrangement. I only put M here to show that, okay, oh, this is for the middle. I am using M as middle here. It doesn't mean anything. I put E here to show end. That is, this one we have at this end, or these three, which are parallel. This is the result. 1.36 ohms. You notice that 1.36 is not up to 3 or 5. Notice that 0.67 is not up to 2 or 1. So, why this 4, which is alone, is carried down? It remains the same. It is now we will find the total resistance for the whole of them. And if you are very observant, you notice that once this one, 2 have become this, these have become this, that means all these 3, 1, 2, 3, are now in series, if you notice. Because this one has become 1, which is this one has become 1, which is this. So this one, this one, this one. Let me show you in the next diagram, then we find the total resistance, the final total resistance now. So this is the new arrangement now. The whole of this have become this. So what arrangement is this now? Series. That means you add them together. That will now be total resistance. That is when I can put T here now. T means total for the whole. Will now be 4 plus 0.67 plus 1.36. And that will give us 6.03 ohms. So that is the answer. Let's have a look at one more arrangement, different from this, but also combined arrangement. Now, we are asked to find the equivalent resistance. I want you to be very attentive to the way I'm going to break this down. You can see that this one is different from the other example. Now, you will look for the free end. We have two free ends here, P and Q. That means you can assume that current is coming from Q, entering the whole of the circuit, then will come out through P. Or you assume that current is entering through P, then it goes through all this and comes out through Q, whichever one. So I am assuming that current is going in through P. It is the direction of the current I will use to know which of these are in series, which are in parallel. Because when you look at them this way, they look confusing. Now, when the current is coming from P, this is a junction or node. Why is it a junction? Because it's a T junction. Anywhere you see T formed is a junction or node. So that means that there is a parallel arrangement there. Whenever you see a T junction, it's a parallel arrangement. That means this one and this one are in parallel. These two and these four are in what? Parallel. So let me write parallel. I'm connecting them together parallel. Okay? So now, but when the current leaves these 2 ohms, on getting here again, this is another T junction, it will divide itself. Part will go here, part will go here, like we have it here. That means this one and this one are in what? Parallel. Parallel, okay? But the current that enters these 2 ohms will also go through the whole of this. 1, 2, 3. That means this 1, 1, 2, 3 are in what? Series. Because the current that enters here will go through all of them. All these 3, 1, 2, 3. That means definitely I can just carve out these 3 because they will be in series. Because the same current will pass through all of them. See. Remember, series arrangement, the same current passes through them. Therefore, I will combine these 3 together to become 1. That means from here now, I'm going to have 2 plus 2 plus 2. That will give me 6 ohms. That means the one inside this loop has become 6. Now, definitely, since this one, which is part of this 6, is in parallel with this 3, definitely this 6 is in parallel with this because 1, 2, 3 have become this. And this one is inside this already. And is in parallel with this. That means 6 and 3 are in parallel. So, that means this one now, these 2, these 2 now, I want to combine them in parallel. That will be 1 over 3 plus 1 over what? 6. Why? Because it is not only these 2 now. It is not only these 2 now. These 2 plus these 2 plus these 2 have become 6. Don't forget. So that means definitely I am finding the parallel between this loop and this loop. Okay? Now, that will give us 9 over 18. But don't forget this is 1 over R. So what will now be R? R will be equal to what? 18 over 9. You turn this upside down, and that will give us what? 2 ohms. That means the whole of these have become 2. Okay? The whole of these have become 2. Now, that 2 now will be in series with these 2 and these 2, because the current that enters here will come through here. So that means we are having 2, 2, 2 again. Don't forget the whole of these have become 2. 2, 2, 2. Okay? Now, that means the second stage now, which is this. Don't forget these 3, these 2, these 2, these 2 have become these 2. So that will now be 2 plus 2 plus these 2. These 2, these 2, and these 2. That will give us what? 6 ohms. Now, since this 2 here is in parallel with this 4, and this 2 is already inside this what? 6 again, that means this 6 and this 4 are in what? Parallel, which will be the last resistance. So that means total resistance now, 1 over RT will be equals to 1 over 4 plus 1 over what? 6. That will give us 1 over RT equals to 10 over what? 24. Okay? So what will now be RT? RT will now be 24 over 10, which is 2.4 ohms. So that means the whole of the resistance combined together, all these resistance combined together will be what? 2.4. So that will be the end of resistors arranged in parallel and in series.